All right, here it is, everyone. How to solve an impossible trig identities question. Now, one of my students, Matt, gave this to me, and when I first looked at this, I was thinking, this is impossible. Why? And before I solved it, I did work it out eventually. It took me like 20 minutes though. But before I explain to you the solution, I think it's really important to explain my thought process, because the goal is not just to solve this particular question. It's to solve any kind of impossible trig identities questions, because you will encounter those. And my thought process was, first of all, okay, which side do I even want to start with? LHS doesn't look like there's anything I can do because it's a square root. And RHS, well, I can do stuff, but how am I supposed to introduce a square root? One thing I was tempted to do was to square both sides, and that removes the square root, but then also kind of changes the question in some sense. So with proof questions, you want to stay away from that typically. So, where do we start? I guess what I did do was I did try to go down the RHS route, because I thought maybe it's something a little bit different. I tried to write this as 1 on cos and this is sine on cos. But then I ran into the problem that I just told you about. I ran into the problem of where do I introduce a square root? How does it just come about? And so kind of like with fractions, it's probably easier to remove a square root than to introduce it. But even removing a square root without squaring it is a little bit tricky. So I had to think outside the box a little bit. What I did think about was, okay, maybe I can't remove the square root, but what other options do you have of removing square root? Well, when you square it, okay, but if I can't do that, if there's already something squared inside the square root, for example, the square root of 5 squared is just a square root of 25, which is just 5, right? So that idea still is okay without having to square the entire thing. And that's the logic that was going on. And I kind of thought, okay, well, how can I introduce a square? There's no squares there already. I can't use my Pythagorean identities. I can't do anything, right? So what I did think about was, okay, how else can we manipulate an expression without changing it? What I can do is, if you think about equivalent fractions, what you are allowed to do is you're allowed to multiply the numerator and denominator by some amount. Because if you multiply this by 2 over 2, that is still 2 over 4, which is still half. It doesn't change the expression at all. So combining these two tricks, I can actually manipulate this to remove the square root. Let me show you. So if you take LHS as 1 plus sine x over 1 minus sine x, what I can do then is I can actually multiply the top and bottom by something so that I can actually remove the square root. And this is where you need to be a bit creative. Initially I tried sine x and that didn't really quite work and get where I wanted to get to. But what you can think about is you can think about, okay, what if I tried to multiply by one of these two things? Because if I multiply, for example, the numerator and denominator by one of those expressions, what that will do and what that will allow me to do is actually remove the square root, because they're both, one of them will be both squared at least. Because I have to multiply by the same expression, I just have to pick which one. And the one I chose was 1 plus sine x. And the reason for that was because, well, I tried it a few times to be fair, but the reason why I ended up with 1 plus sine x was because if you look at this carefully, if you look at the numerator now, that's fine, that's what we expected. We got 1 plus sine x all squared, so I can remove that in a moment. But what I can also do with this one is, if you think about it and look very carefully at this, it's a little bit hidden, but 1 minus sine x, 1 plus sine x, that's actually a difference of 2 squares. I'll continue on over here. That actually just becomes 1 plus sine x all squared over here. That actually just becomes, if you think about it, well, if you expand it all out, it will be 1 minus sine squared x, right? So that would be 1 minus sine squared x. Now that's not a square in and of itself, but what that is a part of the Pythagorean identity. Sine squared x plus cos squared x is equal to 1. And you can rearrange this so that cos squared x is equal to 1 minus sine squared x. So the goal here was to get something squared on something else squared so that I can actually remove these square roots. And now I've achieved that, right? I've got here 1 plus sine squared x all over cos squared x, because here you don't even need these brackets actually. This expression in the denominator is equal to cos squared x over here. And now I have, that's not right, so that should be like that. Now I have over here something squared on something squared. And we know that if I want to take something like this, I can break it up as square root of a, square root of b. And that's exactly what I'm going to do here. I'm going to take the square root of the numerator, so squaring rooting a square already, we just remove that. So that's 1 plus sine x over, and I'm square rooting cos squared x, that would just give me cos x. Important to note though, that's only for certain restrictions of x as well. That's like a whole nother thing, but let's take that for now. And let's roll with it. So we get 1 on cos x plus sine x on cos x. Because then I'm splitting up this fraction, that's really the only other thing I can do. And sec x plus tan x. Okay? Which is what we want to, the right-hand side. So can you see, it goes from something impossible, which seems like you can't do anything to either side, and you just try things. You experiment a little bit, you think about the rules that exist, Pythagorean identities, equivalent fractions, and then ultimately we can actually get to the right-hand side there. And so when something seems impossible, I just want to encourage you guys, hey, just try something. It may not always work. When I first tried the things that I tried, they did not work. But with enough experience and with enough experimenting, you can get well into the solution, even if you don't get to the final step there. But hopefully that's an idea of how to approach impossible trig identity questions there.